Welcome to the third lecture on logical deduction in artificial intelligence. In the previous lecture, we introduced in details what is predicate logic, what is the syntax of predicate logic, and what do we mean by deduction, inferencing in predicate logic. Today, we will study one of the most important techniques of inferencing in first order logic or predicate logic, which is the method of resolution refutation, which is originally attributed to Robinson, his seminal work on resolution refutation technique. To recapitulate, we discussed predicate logic, and in predicate logic we talked about things like for all, there exist, wherever, whenever, someone, no one, and things like that. And we did these 4 examples in first order predicate logic. And we said that in predicate logic we have variables, we have constant symbols, we have predicate symbols, and we have function symbols. And we had 2 new connectors, there exist and for all. And we showed how this first example was coded. We used a predicate goes xy, and we said for all x, goes marry x implies goes lamb x. The second one we said was goes marry school. This was, as we said, an instance which had no variables, so it was called a ground instance. Our goal was goes lamb school, and as usual we wanted to prove this is always true, and by this always true we wanted to say that this is valid, which means it is true under all interpretations. Then we discussed in a little more details about what is meant by inferencing, and we said that first order predicate calculus it is also known as predicate calculus instead of predicate logic. It has a domain, it has some constant symbols, it has some variables, it has some function symbols, and it has some predicate symbols. It has the standard connectors and these 2 additional connectors. We define terms using variables and function symbols. We define formulae using terms and predicate symbols. We discussed what are free variables, which are not bound or not in the scope of any for all or there exist connector, and we discussed bound variables. And then we went to what is an interpretation. And we said that for every interpretation, we define a specific instance of a domain set, and then we map the constants, the functions, and the predicates suitably. And we saw this example as before, and we looked at one domain where we defined this as Akash baby, etc. And we saw examples where we mapped M to some element in the domain, we mapped L to some element in the domain, and we mapped S to some element in the domain. We defined a function gxy in the domain as defined here, and then we could see whether that is true for that interpretation or not. And we could get several interpretations for the same domain, we could get different domains, and our objective to prove that a formula is valid, it must be true under all domains. That means under all interpretations. And a formula is said to be satisfiable if it is true at least under one interpretation. As we can see that the number of interpretations is infinite. So the number of interpretations is infinite. Whereas in a pure Boolean logic, if there are n variables in propositional logic, if there are n variables, there are 2 to the power n interpretations in the truth table of propositional logic. So in propositional logic, If we use propositional logic, then it is finite. But here in predicate logic, we have infinite number of interpretations. So how do we solve the problem in the case where we have infinite number of interpretations? We have also discussed in the previous lecture that this problem is undecidable and there are paradoxes. So it means that it cannot be fully solved, but it is partially solvable in the sense that if a formula is valid, there is an algorithm to find it without infinite time, without going through all the infinite interpretations. So a finite algorithm exists in case it is valid. And one of the most famous algorithms for that is the resolution refutation method. So we will now discuss the resolution refutation method. Before going into predicate logic and resolution refutation with predicate logic, we will first show the resolution refutation in propositional logic and then extend it to predicate logic. So the objective of resolution refutation is we want to prove the validity of a formula F1 and F2 and so on and so forth implies goal. This is our inferencing formula. We will take the negate of that formula. The negate of that formula, if you simply apply the rules, this will become not A or B, and if you take the negate on both sides, you will get this. So if F is this formula, then not F is this formula. And if F is valid, then not F is unsatisfiable. That means it is false under all interpretations. Now we don't want to produce the truth table. So the resolution refutation steps are threefold. First, we will convert it into clausal form. Clausal form is a conjunctive normal form or a product of sums, which means that it will be of the form this and this and this, and each such term, which is called a clause, will be of only or terms. So it's a product of sums. So it is also called a conjunctive normal form formula. So first step is to convert it to a clausal form. Next step is to use the single resolution rule to create new clauses. And the resolution rule says, the method says, that you go on creating new clauses, and if the formula is unsatisfiable, you will prove falsity or you will get a contradiction. So let us see how it works. Let us go to our original example, and from that let us go to this example. If Asha is elected VP, then Rajat is chosen GSEC and Bharati is chosen treasurer. Rajat is not chosen as GSEC. Therefore, this is our goal, Asha is not elected VP. So we choose A to be Asha elected VP, we choose B to be Rajat chosen as GSEC, and we chose C to be Bharati chosen as treasurer. So our first statement is, if Asha is elected VP, then Rajat is chosen GSEC and Bharati is chosen treasurer. So this is our first formula. If Asha is elected VP, then this and this. What is B? Rajat is chosen GSEC and C, Bharati is chosen as treasurer. And if we convert it to a product of sums form, we apply distribution law. This becomes not A or this and this. So this formula would become not A or B and C, which if you distribute this across this, you will get this, which is in the form that we want. The form is that it is a product of some terms. That means it is an AND of some terms, and each term is only an OR term. Each such term is called a clause. So we get two clauses out of this, C1 which is not A or B and C2 which is not A or C. And then the second is Rajat is not chosen as GSEC, which is not B. And goal is Asha is not elected VP, which is G, is not A. And as we said, we have to find not G. So not G is A. So now this one is already in clausal form, this is already in the conjunctive normal form, and this is already in conjunctive normal form. So from this query, we get four clauses. The first is this one, C1. The second is C2. The third is C3, which we get from F2. And the fourth is A, which we get from not G. And the resolution refutation rule says the first step we have now performed by converting it to clausal form. All we have to do is to prove that not F is false. That means we have to prove that this set of clauses is false. How do we prove that? We prove that using what is called the resolution rule. What is the resolution rule? So now we discuss the resolution rule. The resolution rule is, in the simplest case, let C1 be A or B and C2 be not A or C. The resolution rule says if C1 is true and C2 is true, then C3, which is not B, which is B or C, is also true. Which means that if A or B is true and not A, which is the negator of one of the terms, is true, then you can take the other two terms, make an OR of it, and say this has to be true. We could replace B by some clause C dashed and C by some clause C double dashed, and C3 could be C dashed or C double dashed. It is very simple to prove this. All you can do is, if you have C1 and C2, we can prove that C1 and C2 implies C3 is a valid formula. Now to prove unsatisfiability, all we need to do is use the resolution rule repeatedly to reach a situation where one clause is A and the other clause is not A. And since the clauses are all ANDed, therefore this and this reaches a contradiction or false. So the steps are that we repeatedly apply the resolution rule, and if the formula is unsatisfiable, false will be derived. So this is the resolution refutation method. And for propositional logic, since the method is finite, it is terminating, and therefore the resolution rule is sound and complete, in the sense that if the formula is, false is to be derived, it will be derived. We now move on to applying resolution refutation in the same example and just go through it in little more details. So as mentioned earlier, given two clauses C1, which is A or B, C2, which is not A or C, we derive a new clause B or C. In general, B could be another clause C and small c could be another C dashed, and then this would be C or C dashed. We know that this is false, and we go on applying this rule. So given this problem which we had, we converted it to clausal form, C1 and C2. So this is C1, C1, this is C2, this is C3, and we took the negate of G to get C4. And what do we get? If we use C1 and C3, then we have not B and B, so we get not A. So we get C5, as mentioned here, we get not A. Now once we have not A and A, from these two we can get it to be false. So given F1 and F2 and not G, we have proved that F1 and F2 and not G is false, which means that this formula is unsatisfiable, which means that the original formula F1 and F2 implies G is valid or is always true. So this is how the resolution refutation method works. Let us look at another example. The example says Rajesh either took the bus or came by cycle to class. If he came by cycle or walked to class, he arrived late. Rajesh did not arrive late. Therefore, he took the bus to class. So what are the first thing is our modeling in propositional logic. So first thing is identify the Boolean variables. The first Boolean variable is bus. That means he took the bus. Second is he came by cycle to class. The third is he could have walked to class. And the fourth is whether he arrived late or not. So these are the four Boolean variables. What is our first statement? Our first statement says Rajesh either took the bus or came by cycle to class. Now this either or, we could use it as an inclusive or an exclusive or. Let us say we use an exclusive or. So we say he took the bus and not cycle, or he took only the cycle and not the bus. We could do it this way. The other alternative, which is not equivalent to this, is the inclusive or, where we could say he took the bus or cycle. Which in this case it would mean that he could have taken either the bus or the cycle, or both the bus and the cycle. But here he cannot take both the bus and the cycle. So let us assume we have taken this one. The second one was if he came by cycle or walked, he would have arrived late. So cycle or walk implies late. What is F3? He did not arrive late, so not late. What is the goal? Therefore, he took the bus. So this is our modeling. We have now modeled this in first order predicate logic. Now let us get the clauses. So how do we get the clauses? We get the clauses from each one of them. So this is not in conjunctive normal form, because this contains, the way we are saying is that this contains bus and not cycle, or not bus and cycle. Now if we distribute it over this, we will get bus or cycle and not bus or not cycle. We'll get these two, because bus and not bus, bus and not bus, this bus or not bus is true, cycle or not cycle is true, and if something is true, we can simply remove it from a conjunctive form. So this is what we get. From this one, what do we get? From this one, if we move it out a little, we get not A or B. So we will get not cycle or walk or late. So we will, if we get not cycle or walk or late, so we will get not of cycle or walk or late. This is from F1. From F2 we get this, and from this all we need to do is distribute this out, and if we take the negate of this, what do we get? If we take the negate of this, we get not cycle and not walk or late. And if we distribute this across, then we will get late or not cycle and late or not walk. This is now in conjunctive normal form. From F3 we get not late, and from negate of G we get not bus. So what are the clauses that we have got now? So we have now done the first step of conversion to clausal form. So the first clause that we have, C1, is this. The second clause that we have, C2, is this. The third clause that we have, C3, is this. The fourth clause that we have, C4, is this. The fifth clause that we have, C5, is this. And the sixth clause that we have, C6, is this. Now it is not difficult to see how we are going to use our methodology. So let us say we take C6 and C1. C6 contains not bus, C1 contains bus or cycle. From that we will derive a new clause, C7, which is cycle. Now we can use C7 with C5, and if we use C7 with C5, C5 is late or not cycle, C7 is cycle, so we will use C7 and C5 will give us a new clause, C8, which is late. Now we have late and we have this clause C5. I'm sorry, this C5 is not late. So this was C3, sorry. This C7 and C3. C3 is late or not cycle. So, and C7 was cycle. From that we will get C8 is late. C5 is not late. So now C8 and C5 will give me false. So now I have been able to derive false using resolution refutation method, which means that the original formula was valid. Therefore, if I took the negate of the goal and found this formula, that now gives me unsatisfiability. And because it is unsatisfiable, the negate of the formula is false. Therefore, we can now prove that the original formula was valid. We did not use truth table. We just used the resolution refutation method continuously. Having seen the resolution refutation method in propositional logic, in predicate logic we have many other things. We know that we have variables, we have predicates, we have functions, we have constants, and we have the two additional quantifiers. Therefore, while the steps remain the same, the first step is create f dash equal to not f and prove that not f is unsatisfiable. And the two major steps are convert to clausal form and apply the resolution rule. But given the presence of variables, constants, predicates, functions, and the new quantifiers, both the conversion to clausal form, which needs handling of variables and quantifiers and ground instances, And application of the resolution rule in the presence of quantifiers and variables, functions and predicates need more handling in more details. So we first look at how to convert a clausal form, how to get clauses in predicate logic. Here are the 6 steps. Like in the first step of propositional logic, we will remove implications and other Boolean symbols and convert it only having not and or. Then we will move the negates inwards. And when we move negates across for all and there exists, we are going to have the issue of converting and making sure that they are done correctly. Secondly, we will standardize the variables to make them unambiguous. We know that based on scope rules, the same variables can be reused for different scopes. Then we will use a step called scholemization, where we will remove the there exist quantifiers. And this there exists quantifier will either be removed by replacing it with a constant symbol, or if it is dependent on any other variable, it will be replaced by a function symbol. This step is known as scholemization based on the people who have the scholem function. Once you have removed the existential quantifiers, you drop the universal quantifier, so you have quantifier free formula assuming everything to be universally quantified, and then again you apply the distributed law. So we used step 1, 2 and 6 in propositional logic. We will now use all the steps in first order. We now see how we will try and discuss and how we will show the working of the resolution refutation rule in predicate logic in this first simple example that we have had. So our example was as follows. Our example had F1 and F2 implies G. So for that, to prove that to be valid, we will prove F1 and F2 and not G to be unsatisfiable. So for that, we will take F1 and convert it to clausal form. So F1 when converted to clausal form, we will remove this quantifier, this element, and get not A, not goes Mary or this. Then we will have this clause. We will have for all x. We will have not goes Mary x or goes lamb x. Then we have no other steps to do except step 5, where we remove this quantifier and we get our first clause, which is not goes Mary x or goes lamb x. This is or, so it is first clause. From F2 we get our second clause, which is goes Mary school. And from not of G we get our third clause, which is C3, which is not goes lamb school. So we now have 3 clauses. Once we have now converted it to clausal form, we now apply the resolution rule. Now in the resolution rule, when we apply, we now have variables. But we now know that in order to apply the resolution rule, we can resolve this C2 with C1. But in order to resolve C2 with C1, we need to substitute the variable x with school. So if we substitute the variable x with school, this goes Mary school and this not goes Mary school, these two match, and all we get is, because x is substituted to school, we get C4, which is goes lamb school. Now C4 and C3, as you can see, are negates of each other, and therefore from this we get false. So this is just a simple small example by which we can show how we get to do the clausal form conversion and the resolution refutation in predicate logic, where in the clausal form conversion we still, in this example, we did not use existential quantifiers, but we will need to use existential quantifiers in other functions. And this is the conversion to clausal form was straightforward. On the other hand, in the resolution rule, we needed to do substitution of variables with constants, and we will see more critical examples. So having seen this example, we now move over to a more complicated example. So the conversion to clausal form has got these 6 steps. So let us look at this example by which we convert to clausal form. That means let us first identify the brackets so that we are able to. So this is this goes here, and this for all x, this x actually looks at this x as well as this x. So I think there is a need to put one more bracket that will enable us to see, because this third bracket, this x is here, this x is here, this is here, therefore this for all xx has to be satisfied here. So we are have one more variable. So our formula is for all x, for all y, student y implies likes xy. This part, this for all y, implies that there exists a z such that likes zx, this x, and this converts here, and this takes care of this. So in order to do this conversion, in order to convert it to clausal form, we first convert this to not A or B, which means that this gets converted to for all x, not for all y. This not for all is for this whole student y implies likes xy. So this part is this part, or there exists z likes zx. This gets converted, and this sign, whereas this sign is for this, so this sign, this bracket covers this negate sign, and this is for this one. The next, once we have to do, is we need to remove this value, this not all. So in order to remove this, which is student y or likes xy, so we have for all x, not. Now this for all y covers these two, so this will be for all y, and then we will get not student y or likes xy. This bracket gets closed here, this bracket gets closed here, or there exists z likes zx. Now what we have to do is we have to start moving this negate, which means that this negate will have to move inwards. Once this negate moves inwards, this for all will become there exists, and all these will start getting modified. So this will now become this. Once this negate moves inside, this will become there exists y. And then this whole thing will get negated. Once this whole thing gets negated, which means that this will now become student y and not likes xy. Student y and not likes xy, or there exists z likes zx. This bracket gets closed and this bracket gets closed, and this bracket gets closed this way. Now we have done up to here, and we have moved all our negates inside. Negates are all inside. There is no need to standardize variables, but we have two existential quantifiers, this one and this one. And we notice that in these two existential quantifiers, we need to remove these by appropriate new functions or constant symbols. Now in this case, this y is dependent on x because for every x there exists y. Similarly, this z is also dependent on this x. Therefore, we will define two new function symbols, fx and gx. And we will replace y by fx and z by gx. So we will get for all x. Now we will get student fx and not likes x fx, or z will be replaced by gx, or likes gx x. So now we have removed all this. So this step of removal of a Skolem function is by using this mechanism for us to replace it. Now you have to do a distribution because this is AND OR. Now all you have to do is drop the universal quantifier and then do a distributive law as we have seen before. So this is a little intricate because we need to know when and how we are going to remove existential quantifiers. And that is something that needs to be discussed in a little more details, which we shall try to do next. Before we do substitution and quantification, let us look at removal of these existential quantifiers. If we had a case for there exists x for all y pxy, then this under Skolemization, because this x is independent of y, we would replace it by a new function, just a constant symbol pay, for all y pay, which would again get converted to pay, and it would mean that this is universally quantified. On the other hand, if it is a for all x there exists y pxy, it means that this y is dependent on this x. So this gets converted to for all x p of some new function x fx, which in turn gets converted to p of x of x. So this is how we apply the Skolemization rule. So this is called the Skolem function. Now once we have converted to clause form, as we should see, we now want to apply our resolution rule. Let us see us having these four clauses, C1, C2, C3 and C4. Now we can see C1 and C2 can be unified. C1 and C2. In order to unify C1 and C2, in C1 we could replace X by Madan and Y by Z, and we will get a new clause which will be passes Madan Z. We could also replace Z by physics, and we could unify C1 and C2 and get passes Madan physics. Out of these two, this one, let us call it C dash, and let us call this C double dashed. C dashed is more general than C double dashed, which means that C dashed is more general because the number of cases that C dashed can cover is much more than what C double dashed can cover. So our objective is to find a more general clause, and in general we want to find between two clauses what is the most general derived unified clause that we can get. So let us look at C1 and C4. Given C1 and C4, we could replace W by Chetan or Madan, and we need to replace the Y by mechanics. On the other hand, the more general of C1 and C4, the more general one would replace Y by mechanics, and once we replace Y by mechanics, we will derive, and we will get passes and not passes here. So we will derive not studies X mechanics. And now if we have this as our C triple dashed, then this not studies X mechanics. So C2 and C triple dash, by a substitution of X as Madan and Z as mechanics, would give us false. Will these two unify? No, because this does not unify if I try to replace, though both are in the same. So this is how I get this. So in the repeated application, we must ensure that we unify by the most general unifier. And once we use the most general unifier, it will be easy for us to use less number of steps for us to derive the null clause or the false clause if the same exists. Now we have seen one example. Let us try and solve two other examples that we had done before: the contractors and the engineers and the dependable example, and the Ayesha and the dancer example. So this is our example. We had for all X, contractor X implies not dependable X, and then we had there exists X, engineer X and contractor X. That means some engineers are contractors, and we want to prove that there exists some engineer who is not dependable. In order to simplify ourselves, let us use contractor X as Cx, dependable x as dx, and engineer x as ex. So if we convert f1 to clausal form, what do we get? We get for all x, not contractor x or not dependable x. So we get for all x, not cx or not dx. And if we remove this for all, then we get this as C1. From F2, what do we get? We get there exists x, engineer x and contractor x. And because of this there exists, we will now have to use the Skolem function. So we will use the Skolem function and we'll replace this by a constant, and we'll get ex and ea and ca. Because x is not dependent on anybody, therefore we get two new clauses, C2 and C3. From not of G, if we do not of G, then what do we get? We get not there exists x, engineer x, and not dependable x. If we take the negate inside as per our rule, we get for all x, not of ex or dx. And we remove the for all as per our rule, and we get this as C4. Now we can start using our method of resolution refutation, and the simplest way in which we can start doing resolution refutation, we can take C2 and C4 and we replace x by a, and we'll get dA. Then this new clause C5, which is dA, we replace a, and with C1 we replace this, and we get not CA. We get C6. Now C6 and C3 will give us false. So this is the steps. We convert F1, F2 and not G into clausal form, and then use the resolution refutation rule. Let us go to the Ayesha and the dancer example. We have F1, F2, F3 and F4 and G. So for F1, what do? F1 is like before. We get for all x, not dancer x or graceful x. And we can remove this, and this becomes C1. From F2, we get student Ayesha. This becomes C2. From F3, we get dancer Ayesha, which becomes C3. And not of G again becomes not of there exists x, student x, and graceful x, which becomes for all x, not student x or not graceful x, which becomes C4. Given all these, now we start our resolution refutation. We have C1, we have C2, we have C3, and this is removed, and we have C4. So we start applying the resolution rule. We can combine C4 and C2, and by substituting s by a, x by a, we get not of GA. With this one, we apply this result with C1, and here again we replace x by a, we get not of dA. And this one with C3, which is already dA, we get false. So we see that in predicate logic, the resolution refutation method is working in the following way. It does the following steps, and the steps are: 1. Convert to clausal form. We defined how the 6 steps will convert it to clausal form. The second, but before the 6 steps, we do F1 and F2 and so on and so forth, and not of G. And then we apply the resolution rule. And in this resolution rule, we need to do substitution and unification. And we need to use the most general unifier. And we repeatedly apply the resolution rule to prove unsatisfiability. As we mentioned in the previous class, first order predicate calculus and this resolution rule is semi-decidable in the sense that if the set of clauses are unsatisfiable, this will terminate in finite number of steps and prove it to be unsatisfiable. However, if it is not unsatisfiable, that means it is satisfiable, then the algorithm may terminate or may not terminate. Because as we have seen in the paradox, this is an undecidable problem. This is semi-decidable. So in this lecture, we have discussed the very world famous resolution refutation mechanism, which is a very simplified single step algorithm using only one rule called the resolution